processes and for living cells that change their shape and volume depending on the salt concentration. And of course, for optical clearing of biological tissues when the tissues are saturated with osmotically active agents, so they can change their shape and their volume. And these processes can be measured in real time using a special developed technique. So we used an approach based on phase resolved OCT. I won't stop much on the details of this approach. It is just briefly described here, and I refer you to the comprehensive publications devoted to the um, technical details. Just briefly to show you, we have our OCT probe working in non-contact mode, and we have our object, a tissue. Um, at the start of recording, we put a certain amount of liquid, osmotically active liquid, on the surface of an object to excite um, deformation caused by the concentration gradient. So this amount of liquid and its concentration remains constant during the whole process. And so we have our structural OCT information and phase variation map. And using these phase variations, we can obtain interframe strain maps. This strain can accumulate during the set periods of times. It can be minutes, seconds, minutes, and tenths of minutes. So further, I will refer to this kind of result, to the interframe strain, to demonstrate the osmotically induced um, deformations, the corresponding strain maps. So here are the parameters of a system. Well, the easiest way to study some um, deformational processes by optical techniques is to use objects with the controllable properties. So we tried polyacrylamide gels. Um, they have high turbidity, high scattering intensity, and here are some details of their preparation. We prepared them to have a different cross-linking degree. It is shown here. So what is important here is a number of cross-linking. So with increasing number, the number of cross-links actually decreases. It is shown here on the scheme. So with increasing number, the pore size increase and the number of cross-links uh, decreases. These gels were prepared with equal hydration level and various cross-linking degree to check um, the dependence of osmotically induced deformation on this amount of cross-links. And then the gels were exposed to 50% glycerol diffusion. So we just dropped glycerol on the surface of each kind of gel and recorded a deformation map. So here the results are present in like waterfall diagrams. We have strain here on the vertical axis, and we have time dimension, and we have also depth resolved axis here. So it is time and it is the depth of the sample, and vertical axis is strain. And also strain is reflected on the color scale here. So blue color means tissue shrinkage. So it is negative sign strain, and the yellow and red color means tissue dilatation. So what we see here as a result is that this osmotically induced strain strongly depends on the cross-linking ratio, and with the um, decrease of the number of crosslinks, the osmotically induced shrinkage intensity noticeably increases. So already for the first minute of diffusion, we see that the a sample with a high amount of crosslinks, it has positive sign deformation and negative sign deformation. It is more or less stable to the action of glycerol, and this one um, 7 to 1 ratio of crosslinks, it has very strong osmotically induced shrinkage. And for 5 minutes of diffusion and 10 minutes of diffusion, this effect just becomes more and more evident. So this result is reasonable because when the pore size increases, liquid is easily released to the solution. I mean, the liquid that is present in this objects. So it easily diffuses, easily releases to a solution. So that's why we see increasing osmotically induced shrinkage. This some quantitative results of the same measurement. It just confirms that the strain minimum just drops according to the increase of this cross-linking ratio. And for the first three types of our gels, this is a quasi-linear dependence of the strain minimum on the degree of polymer cross-linking. Between these two ones, these two terminal ones, the difference is not such dramatic. But here we have a quasi-linear dependence. So by building these plots, we can just do the opposite to take um, gel with a known cross-linking ratio, measure its strain minimum during the diffusion of osmotically active agent, and just to determine approximately the ratio of cross-linking, which is quite an interesting result. So this osmotically induced strain minimum can be a kind of indicator of the cross-linking degree. So the amount of crosslinks, the cross-linking, is a characteristics of many polymers, especially biopolymers. And we try to check this obtained result on some biopolymers to know if we can obtain some diagnostically useful information. So one of the biopolymers we have experience in our lab is cartilage. So the general structure of its matrix is here in the picture. It is a collagen-rich tissue with a specific cross-linker protoglycan molecule that maintains the tissue integrity and maintains the hydration level of a tissue. And each pathology actually is connected to the depletion of this protoglycan component. In ex vivo experiment, we can model this depletion using the special enzyme trypsin. So it is the next picture. By increasing the time of reaction with trypsin, we can just simulate several stages of cartilage degradation. With this resolution, we cannot see the fine structure of cartilage matrix, but we can see the cells. We can see that with the increasing time of trypsin reaction, the cells are becoming smaller. And the intensity of histological staining decreases. So we have some gradual process of protoglycan depletion. And with cartilage, we did the same experiment. We dropped glycerol of 30% concentration and measured diffusion for 10 minutes and all the deformation related to this diffusion. So we have OCT maps, and also the structure of the tissues was verified using conventional histology with the staining specialized for protoglycan. So it's Elsan blue here and safranin O. So this histological stains just have a reaction with protoglycan. So the intensity of color is proportional to protoglycan content. What we see here that healthy tissue control here has the same sign alternating nature as a polymer with a high content of cross-links. So it's subsurface dilatation followed with some shrinkage caused by liquid outflow to glycerol solution. And it has good intensity of staining by um, histological um, chemicals. Uh, 2 hours of reaction of trypsin lead to some alteration of a structure. So here, according to histology data, a structure is preserved in the middle of a sample, but on the borders where there was a contact with the solution, um, the intensity decreased. So we can see here. So it means that protoglycan here are partially depleted, not totally, but to some part. And a strain map also changed dramatically. Um, extensive blue color here means that we have an increase of shrinkage, of osmotically induced shrinkage. So it means the decrease of cross-linking degree and the increase of the rate of water outflow. For 5 hours, um, this process continues. The structure is altered, so we do not see the preservation of structure in the middle. So the whole volume of a sample is altered by enzyme, but we have some intensive diffusion, again, intensive osmotically induced shrinkage of a tissue. It means that some amount of water still remains, is present in this tissue, and it can respond to our to the excitation of osmotic deformation. And for 24 hours, there's no such a big difference in histology samples, um, in histological samples. So we see the further change in staining intensity as for Asian blue and safranin ore, but for strain maps, the situation changed dramatically. So there's no more this extensive shrinkage. And if we see the quantitative data, so for the healthy tissue, this shrinkage minimum of this shrinkage is about minus zero point 0.1. Then for the partially depleted protoglycan, it drops to minus zero point 0.3. And for the totally depleted protoglycan, so here for 24 hours of reaction, it is almost totally depleted. The amplitude of the observed shrinkage is even smaller than for the healthy tissue. So histology shows us the structure in terms of protoglycan content. And OCT strain map shows us the structure in terms of its reaction to external excitation of mechanical process. So these data are a little bit um, different from each other. This uh, Using histology, we can see the information about the content of the matrix, and using strain maps, we can see how this matrix just react to the external mechanical excitation. So here it is some numerical data. Again, the table with the strain minimum. So this is statistically significant difference between um, different types of these degraded tissues. And also we built distributions, depth resolved distributions of strain along the line here on the strain map. So we can distinguish in a quantitative way, we can distinguish between these types of tissue. I would like to stress here also that using OCT structural data, it is almost impossible to see the difference. Um, so using the scattering intensity, we can see that they are more or less the same. But when we have a strain map of osmotically induced deformation, we can clearly distinguish between them. So this technique can be used as a potential tool for express diagnostics of mechanical response of these tissues to external um, excitation. Well, finally, I would like to show the possible applications of this technique. Osteoarthritis of joint cartilage is a very famous problem. So the mechanism of its development is just the same. It starts with proteoglycan depletion, and the measurement of proteoglycan is not a trivial task. So this technique may give additional information during conventional arthroscopy, for example, to grade the stage of a disease and to give some prognosis of its development. And another interesting application can be the use of these tests for checking the quality of autologous costal cartilage implants. These types of implants are usually taken and implanted to the same patient, and in a very short time, so in a few hours, and there's no time for histology, there's no time for MRI or any time consuming diagnostics, but using our express approach, we can just check the quality, the mechanical response of this tissue to the osmotic excitation, and we can predict the maintaining of the main function of cartilage, so how the tissue can just respond to external mechanical excitation. And for conclusions, I have several points. First of all, um, osmotically induced deformations can be visualized in real time using the specially developed approach by optical coherence elastography with the following parameters and resolution of 50 micrometers. This measurement can be carried out within the first 10 minutes of diffusion, where there is the highest intensity of osmotically induced deformation. For the polymeric gels, we observed that the rate and the amplitude of shrinkage and dilatation depend on the degree of cross-linking. And for cartilaginous tissue, we observed that the osmotically induced distribution of strain is a tool to reveal the degree of proteoglycan depletion. And this is a potential tool of express diagnostics of the early or even late alterations of of a tissue. I would like to thank my colleagues from different scientific organizations who, in direct and an indirect way, participated in this work. And I also would like to show some related references, our recent publications and works on this topic. And thank you very much for your attention.
Thank you very much, Yulia. Let's thank the speaker. Unfortunately, we are out of the time, and
Oh,
we have
I'm sorry.
to move to the next speaker. So please. So, and it is my pleasure to announce the next speaker, Dr. Bratashov from Saratov State University, with the invited talk, the peculiarities of photoacoustic signals from CTC, tumors, and blood vessels of immunocompetent mice. So, please. Um,
Oh, sorry for the problem, and thank for the nice introduction, and thank to for the invitation to this conference. And so the topic of my talk is the peculiarities of acoustic signals from CTCs of immunocompetent mice. The talk is based on the article that was recently published, and our work is devoted to detection of circulating tumor cells of melanoma in the blood of the patient in the perspective, but now we are mostly working with the laboratory animals, and we are mostly working with the mice with working immune system. So the cells we want to detect looks like this in the blood, and we are developing various type of devices to detect these cells in blood, minimally invasive, and making in vivo flow cytometer based on optoacoustic signals that works with the human patient, with laboratory animals, and with the cultural cell in the flow of the blood or flow of more transparent liquid. The main concept of the device is shown here. We use pulsed laser. In the main device we have the pulsed laser with selectable wavelengths. We first used injection of cultural cell in the blood of the mouse through the carotid artery, and detection and the base of the animal feet in the large vessels through the skin. And so we are getting the depth signal. It's looking like this at the top left part of the image. The main signals are on the over the signal of the vessel, this part. And we have also sort of echo signals somewhere in the depths of with some delay. We don't completely sure about the nature of these signals. Maybe it's some reflection, and maybe it's some making of bubble in the blood flow and then closing down this bubble in the blood flow. Then we draw the usual for the in vivo cytometry graphs of some signal. In our case, it's the photoacoustic intensity with high frequency over this blood flow signal, the signal from the vessel, versus time. And we count the number of the signal, we measure the intensity of the signals and so on. So the source of the signal is small particles of melanin grains that usually has some submicron size. Here it's highlighted by the Raman spectroscopy, by the main peaks of the melanin. It's quite varying from one cell to other. So we are trying to make some conclusions about how the photoacoustic signal from the cells is generated. We had to develop quite a complex model when we cultivate the cells with the same. We trying to cultivate the cells of the same time, with the same temperature, with the same environment. And then when we get the number of cultural cells of some day of cultivation, we can inject it into the blood flow of the mice and measure the signals in controllable way. And we are mostly focusing on the blood signal part of the signal. And as the grain is very small, we have a very small high frequency component somewhere here. And then we try to measure some statistics. So we have the signals, the traces, the dependence of the signal intensity versus the time, and we can measure various characteristics. For example, we can, the simplest and the easiest, we vary the energy of laser, and we see the intensity of signal increasing, the number of signal increasing. It has some small threshold. Below this we have no nonlinear photoacoustic signal, and then we see the increase of signal via when we increase the energy of the laser, the less colored, the less rich of melanin cells become also the source of nonlinear signals, and we see the increase of both intensity and the number of signals versus the pulse energy. It also depends on various pulse parameters. The most prominent dependence is the length of the pulse, and the sub-nanosecond pulses work slightly better than the longer pulses in our case. It also depends on overheating, so the pulse repetition rate play an important role, but we cannot increase it a lot. If you have pulse repetition rate below the something like 100 Hz, we will have a problem that we will not get signals from all the cells. It's sort of flow time against the laser beam. And if we have pulse repetition rate something like 10 kilohertz, then we clearly see overheating of the skin. and damage of the skin. And it's it's over the allowed energy for the patient. It's non-healthy variant, so we mostly focusing on pulse repetition rate, something like 1 kilohertz or 2 kilohertz obtainable either with solid state lasers or with lasers by PG Photonics that based on that is slowed down based on fiber. So mostly it's either overclocked solid state laser that makes 1 kilohertz at high energies, or slowed down fiber laser that downclocked to 2 kilohertz rate. And we have something like this in dependencies. So it's statistic of signals and number of signal. With the energy of laser, it's growing sort of linearly, and then the intensity go to some threshold, maybe the source of this threshold that we just blow all the cells containing melanin in the flow and making bubbles in the blood flow. We have seen it when we are working with small vessels near the skin by the microscopy technique. This variant, but mostly it's in the depths and it's not so destructive variant. And we also measure dependence from various parameters of the laser, trying to develop the best possible combination of the pulse duration, pulse repetition rate, and maybe some other parameters. So this scheme working with various animals, with the human, we can work with with healthy volunteers. At this variant, we can work with the animal, and we can work with the culture cells in the flow. So we are mostly tested with the healthy volunteer that we have no side effects, no overheating at these parameters. We tested with the animals most of the pulse parameter dependence on the generation of signals to evaluate some parameters for model for the human patient, because it's sort of complicated task to obtain the required energy at the depth of the vessel without the overheating the skin and without going over the allowed energy density on the level of the skin that is sort of 10 times smaller than the energy where the overheating starts. And the overheating really starts at these parameters. And so now we have sort of model for the patient, and we have working variant to work with animals, with mice that has injected culture cell with the repeatable good defined parameters, with the natural cancer developed at the various stages. We also confirmed this by the photoacoustic tomography, and we see the development of the primary tumor that is source of the cells. Here it's at the early stage, and usually it will be something like 1 week when we will see the pictures that I show. we try to induce the tumor in various internal organs of the animal, and we see something like this, a lot of circulating cells at the late stages that correspond to this sort of images. But it's very late, very developed tumor in black immunocompetent mice. And we also make some additional devices that can extract either cells or artificial objects from the blood flow, and then we are making some sear substrate to get the signal from the depth of the cells and to see what happens inside the cell, makes sort of search probes for intracellular measurements. So we are measuring the extraction of the object from the blood flow and the rates of magnetic separation where it's effective. And so I would like to thank all the people who were involved in RSF grant and mega grant given us to develop this sort of device, to make these experiments. Thank the audience. That's all for my presentation.
Thank you very much. Let's thank the speaker. And thank you to be in time. So, questions, please. Yes?
I have a question. Maybe I lost some part of information, but you did not say anything about the pike energy density in the focus of your laser.
It's quite high. At the skin level, it's it usually
Раз, два, все работает.
it's usually the maximum allowed density by the regulation. And with animal, we sometimes trying to got into the higher energy density. We try it up to 10 times before up to the energies when we start to see the signal from the skin, from the overheated small vessels.
Yeah, but it's not a question about overheating. There's a problem of the damage of the healthy cells by the radiation, because the density of this radiation can be much higher than the damage threshold for the even healthy cells. This is the problem.
We have a regulation, and it's quite low, about the maximum level of the skin, and below the skin it's regulate all the damage mechanism, and we have tested all the damage mechanism, appearance of erythema at the place where it's irradiated, the damage of the blood cells by this level of energy. We do not see effects of damage if we don't have the melanoma cells. With melanoma cells, we sometimes see sort of blowing of the cells by the excess of the energy. We see that the part of the vessels become empty, and then the blood flow restores in this vessel, so we don't damage a lot this vessel. It's restored blood. It was in mouse ear. It was sort of usual in vivo cytometer that based on the transparent microscopy. So we have usual in vivo microscopy in the ear where we see the vessels, where we see the blood cells flowing, and at the same time we measuring the photoacoustic signal from these cells. This is maybe non-healthy, and it has if it will be played for, we not sure if the blown out cell make more damage for the patient when all its content is blown, roasted by the laser and then flowing down, and some nuclear acid information maybe will be flowing the open blood flow from these melanoma cells, or the intact cell will flow down, captured in the small vessels of internal organ, and then become the source of secondary tumor. And we are mostly focusing on, if we are working with patient, we are thinking about monitoring how the cure, if usual cure for melanoma affects, because the tumor is changing, and sometimes the patient is cured by at the start of the application of usual methods, and then the optical sorry, the tumor is changing.
Okay. So, thank you very much.
Okay, let's thank the speaker again. And we have to move further. Dr. Skibina. Online? Is the next speaker is here? No? Maybe online? So, doesn't know the speaker? Она не онлайн, точно? Не согласен. Онлайн нет никого?
Нет.
Скибина.
Так, Яша, Валерий, Виталий, Владимир. Арсений. Нет таких?
Она не предупреждала, что онлайн будет.
Нет? То есть там кто онлайн, они предупреждают, да?
Да, обычно она не предупреждает.
Okay. So let's move to the next speaker. Dr. Tankanak from the Institute of Cell Biophysics. It's also the invited talk, the effect of local heating on continuous hemodynamics, regulation of upper and lower extremities in type 2 diabetes mellitus. So please.
Good day, dear Chairman. Good day, dear colleagues. I want to thank the organizers for invitation, especially for Professor Priejev, and want to talk about effects of local heating of cutaneous hemodynamics, regulation of upper and lower extremities in type 2 diabetes mellitus. Sorry. The human cardiovascular system is a closed system in which oscillations of various nature take place. There are two non-invasive techniques for studying peripheral hemodynamics in the skin. The first one is photoplethysmography, which provides information about, about skin blood volume. And the second one is a laser Doppler flowmetry, which provides information about skin blood perfusion. As you can see in the picture, both signals from photoplethysmography and signals from laser Doppler flowmetry have oscillation with different frequencies. Some of them related with cardiac output and breathing, and the other ones reflect the function of local regulation mechanisms. Fragments of two signals recorded simultaneously are presented here. You can see some synchronicity. Synchronicity between both signals. We suggest that interactions between oscillatory processes in cardiovascular systems can be disturbed in pathologies, and analysis of all signals recorded simultaneously, which provide the basis for new diagnostic criteria for assessing of cardiovascular system states. The pathology I am going to talk about is diabetes. Diabetes mellitus is a chronic metabolic disorder characterized by persistent hyperglycemia. It won't be due to impaired insulin secretion, resistant to and it may be due to impaired insulin secretion, resistance to peripheral actions of insulin, or both. Chronic hyperglycemia in synergy with the other metabolic aberrations in patients with diabetes mellitus can cause damage to various organ systems, leading to the development of life treatment complications, most prominent of which are micro or macrovascular complications. I will talk about these related to the peripheral vascular bed. The heating test is a functional test to study the response of a microcirculatory channel to a stimulus, local heating of the skin area, local thermal hyperemia, which is widely used to assess the neurovascular and endothelial function of skin microvessels. And in patients with diabetes, thermoregulation is impaired, which may lead to reduced vasodilation in the skin of extremity due to development of neurovascular dysfunction. So the aim of our study was to assess changes in spectral components and phase relationships between tissue blood volume dynamics and skin blood flow oscillations in upper and lower extremities of healthy volunteers in type 2 diabetes mellitus patients to respond to local heating. 44 subjects participated in the study, 22 healthy persons and 22 patients with diabetes. The physiological conditions of all participants are presented here. The healthy persons had not taken any drugs for at least 1 week before the study, has no any chronic or acute illness, and their patients will take in standard therapy. The illness of disease was about 10 years and more. The registration was carried out in a quiet room at normal temperature after 20-minute adaptation. Subject was in supine position during registration. Skin blood flow was recorded by laser Doppler flowmetry with two infrared probes from two skin sites. One probe, the first probe was placed on the The skin blood flow was registered from forearm and foot, as presented here, and the tissue blood volume was registered with photoplethysmograph angioscan with two light-emitted diodes from two sides too. From second finger of right hand and the second finger of right foot. We use the following study design. During first 15 minutes, we use the following study design. During the first 15 minutes, we registered basal level of signals at rest under 32 Celsius degrees. Then, when we switch on heating, and when we switch on the heating of both skin areas at a rate of 16 degrees per minute. Heating elements were combined with laser Doppler flow meter probes as presented in the figure. After reaching 38 degrees, the heating was kept up until the end of the recording procedure. To avoid transition effects related with axon reflex mechanisms, we analyzed only the first and the last 15 minutes fragments of all signals. We carried out spectral analysis. We analyzed spectral components in 5 non-overlapping intervals, oscillation in which are associated with various physiological processes in the cardiovascular bed as presented here. Also, we estimated the degree of correlation between phases of analyzed signals with the value of wavelet phase coherence function as presented in the slide. Wavelet phase coherence was calculated for each analyzed frequency. Let me go to the results. The amplitude of myogenic respiratory and cardiac oscillation of forearm and foot skin blood flow were higher during heating in healthy patients as compared to rest. Otherwise, the amplitudes of endothelial oscillations were low during heating in patients as compared to the rest. We suggest that differences of answers in endothelial interval can be related with development of endothelial dysfunction in diabetic patients who have more than 10 years illness duration. For tissue blood volume dynamics, we have the follows. In both groups, we have decreasing of the cardiac amplitudes on forearm under heating. Also, we observed increasing neurogenic, myogenic, and respiratory amplitudes in controls in response to local heating for foot tissue blood volume, but no significant differences in diabetics. This result may be explained by the presence of neuropathies, decrease in myogenic vascular tone, and changes in the venous part of vascular bed in diabetics. Wavelet phase coherence between skin blood flow and tissue blood volume dynamics is shown in this slide. You can see that we obtained significant decreasing of phase correlation between these signals in neurogenic interval under the local heating of on both extremities in control group, and increasing phase correlation in respiratory intervals on the foot in diabetics group. The result of phase correlation analysis of the same signals on the different extremities is presented in this slide. There are no difference of phase correlation for tissue blood volume, nor in controls, neither in diabetes. And for phase correlation of skin blood flow, we have different heating effect for controls and patients. In control group, we observe decreasing. In control group, we observe decreasing of correlation in neurogenic and myogenic intervals in response to local heating. In contrary, in type 2 DM group, we obtained increasing of correlation only in neurogenic intervals under heating. This result may also prove the presence of neuropathies and decrease in myogenic tone in diabetics. So let me go to the conclusion. The spectral components and phase correlation couplings between tissue blood volume dynamics and skin blood flow oscillation in the upper and lower extremities at rest and in response to local heating in healthy persons and diabetic patients were revealed. Were investigated. Significant changes in spectral components and phase relationships between tissue blood volume dynamics and skin blood flow oscillations in response to heating in healthy subject and diabetic patients were revealed. The approach based on the comprehensive analysis of simultaneously recording physiological signals provides better understanding of regulation on blood circulation. And we believe the result obtained can provide the basis for development of methods for early non-invasive diagnosis of microvascular disorders and ways of their therapeutic correction in various social significant diseases, including diabetes. Thanks for your attention. I tried to quick presentation.
Yes.
Thank you very much for your interesting presentation. I have two short questions. First, how much the effects depend on the locality of the measurement? So you chose the extremities, yes, lower and higher. But if we measure the forearm or on the forehead you receive similar dependencies?
We choose the upper and low extremities for the following reasons. We know that the most damage we have in upper extremities because we have vertical position normally, and in diabetes we have some damage in upper in lower extremities, and we choose only upper and lower position, upper and lower extremities for this reason. Maybe in head or in no. I think I know that we can measure laser Doppler flowmetry signals from head, but I have no idea about.
So you didn't study that. The second question is, can you identify the stage of the diabetes mellitus disease? For instance, in your groups, the duration of the disease was more than 10 years. Yeah, but if it is below 10 years, smaller, shorter time, or the glycation index. Some people have compensated diabetes. Some people do not compensate. So, are there any differences in the signals?
Thank you for very interesting question. It's a more interesting question. We have our patients were in standard therapy in hospital and has comprehensive situation and have no high sugar level because he has a therapy. We can't to measure our signals in acute stage, unfortunately, but we can't to identify the stage of disease.
Okay, thank you.
It's very interesting, but not possible, unfortunately.
It seems that it's most not for early diagnostics of diabetes, but for for assessing the damages of blood vessels.
We want to provide early diagnostic, especially for this for this goal too. We investigate the ethics and want to provide the medicians some new diagnostic methods.
Thank you. Would you please show the 9th slide? There is some changes in the dynamics in resting stage. Yes, yes. As I understand, there are some changes in the dynamics in the resting stage. Yeah, in the first. Why is it happens? This is controls. So.
Forearm, foot, control with blue.
Yeah.
You talk about.
We see it. Yeah, the raising of the blood perfusion during the resting stage. But the temperature is still, as I understand, the same.
It's the same, but to standard conditions, we hit in this stage 2, but not for 58 and for 52. Maybe during slow heating may affect in this.
Okay.
In this temperature too.
Okay. This is low heating also. Yeah. Thank you.
To standardize all signals, because time to time the temperature in room was different.
Yeah. Okay. Thank you. Are there any more questions? No. Okay. Let's thank the speaker again, and let's move to the next talk. is there Dr. Lubimsky? Okay. Hello, so please. Your presentation. So, and I'm happy to announce the next speaker, Dr. Lubimsky from Prokhorov General Physics Institute. And the title of the talk is Quantum Chemical Modeling of Structure and Raman Spectra of L-lactide and epsilon caprolactam oligomers.
Подсвечивать? Звездочку, все, спасибо.
So,
Good morning, ladies and gentlemen. My name is Sergey Lyubimovsky, and now I introduce you my presentation dedicated to... Еще раз? Все, хорошо. Sorry for a little delay. Well, my presentation is dedicated to quantum chemical modeling of structure and Raman spectra of L-lactide oligomers. Ближе к микрофону. Хорошо. My presentation includes motivation and objective of the study, methods of the study, experimental results, results of quantum chemical modeling, and also conclusions. So, poly-L-lactide and poly-L-lactide based materials are biodegradable and biocompatible polymers. It means that it can be decomposed on substances which are neutral and harmless for people and nature. So these materials are widely used as, on the one hand, disposable tableware and food packing, and on the other hand, as bioresorbable medical implants, scaffolds, and nanocarriers. So the objective of this study is determination of dependence of poly-L-lactide or PLLA based materials, Raman spectra, on length of monomeric units sequences. This objective is more global. Now I tell you about some local progress in this. We use two groups of approach of methods, both experimental and theoretical methods. Our main experimental method is Raman spectroscopy, which is a non-destructive and highly informative method for study of molecular and supramolecular structure of such polymers. In details, we used Raman spectrometer Centera 2 with excitation wavelength of 785 nanometers. Geometry of scattering is 180 degrees. We use objectives with 20-fold and 50-fold magnification. And last but not least, we use spectral resolution is 1.5 reciprocal centimeters. In addition to the experimental method, we use theoretical approach because we need to specify our molecular structure and interpret vibrations, in particular Raman vibrations, and we use density functional theory. In details, Priroda program, this is Russian program, so Priroda. Alib functional, which is based on general gradient approximation, and expanded 4Z basis set of Gaussian functions. This is implemented in the program. So, now it's turn to the experimental part of the work. On the slide, you can see Raman spectra of the PLLA samples with different crystallinity degree in the spectral region from 18 to 980 reciprocal centimeters. We established that in this spectral region, spectra of these samples are very sensitive to the change of the crystallinity degree, and when crystallinity degree decreases, spectra change dramatically, and I marked rhombuses, lines, some lines which are very sensitive to this change. And these specifications we can use for construction of method of estimation, evaluation of the crystallinity degree of these substances, of these samples. How we do it? Sorry. We consider the ratio of the peak intensities of some bands, namely of the bands at 411 and 874 reciprocal centimeters as a function of the crystallinity degree. We found out that this dependence is monotone and can be used for evaluation of the crystallinity degree of these samples. And now, on the slide, you can see some added series. 3 days ago, my dear colleague, Dr. Novikov Vasily, told you about copolymers of L-lactide and epsilon caprolactone. Maybe you remember that presentation. And if we joined these two series, we can see that approximation is good for linear. So, on this slide you can see Raman spectra of discussed samples, but in another spectral region from 1215 to 1950 reciprocal centimeters. The main attention I ask you see on the trident. This is related to the stretching vibrations of carbonyl group in the molecule of L-lactide. So, when the crystallinity degree decreases, this trident dramatically change this form to the more smooth shape. And this is very interesting fact. And on this slide you can see Raman spectra of the discussed samples, but in another spectral region from 2500 to 3300 reciprocal centimeters. We found out that Raman spectra of these substances, of these samples in this spectral region are not very sensitive to the change of the crystallinity degree. Now it's turned to the theoretical part of our work. In the center of the slide you can see the molecule of poly-L-lactide, the monomeric unit, and our first step is modeling of the structure. Now we modeled the structure of decamer, so 10 monomeric units of L-lactide in the conformation of helix 10-3, which means 10 monomeric units to 3 turns. Because this conformation is the most stable in our physical conditions. Also, we consider different positions of terminal hydrogen atoms, and we established that, namely, this structure with 2 intermolecular hydrogen bonds has the lowest total energy. So, after modeling of this structure, we calculated Raman spectra and broadened it according to the experimental data. Namely, we use the experimental Raman spectra of PLLA sample with the largest crystallinity degree what we have, 86%. And now on the slide you can see the comparison of experimental and theoretical spectra with in the spectral region from 80 to 980 reciprocal centimeters, and we see that the most intensive, the most informative Raman bands coincide. On this slide you can see the same comparison, but in another spectral region from 1415 to 1950 reciprocal centimeters. And in this spectral region, experimental and theoretical Raman bands also coincide. Now, comparison is in the another spectral region from 2500 to 3300 reciprocal centimeters. In this spectral region, shift of the theoretical Raman spectrum, relatively the experimental Raman spectrum is more than in the previous cases, but it can be explained by, well, features of using a harmonic approximation, and this is normal situation, but we also can see that the most intensive, the most informative Raman bands in this spectral region coincide. So, the conclusions are, firstly, the ratio of the peak intensity of the poly-L-lactide bands at about 411 and 874 reciprocal centimeters can be used for evaluation of the crystallinity degree of different poly-L-lactide based materials, including neat poly-L-lactide. We found out Raman bands which are sensitive to the crystallinity degree and consequently to changed stereoregularity. And the second one, broadly calculated Raman spectrum of L-lactide decamer in the conformation of helix 10-3 is in good agreement with the experimental Raman spectrum of the neat poly-L-lactide with the crystallinity degree equal to 86%. We assigned all the most informative Raman bands in the mentioned experimental spectrum of the neat poly-L-lactide. So my presentation is over. Thank you very much for your attention.
Okay. Oh, there are questions, please.
Thank you for your talk. Please switch to the previous slide. No. Yeah. The spectral resolution of your equipment is 1.5 reverse centimeters. The shift between experiment and theoretical research is about 100 reverse centimeters, or maybe 15. It's huge compared to the spectral resolution. It is it any systematic effect or the error of approximation?
Well,
from
as
your word, I consider that is the last case, but maybe it's something.
Well, as I said, this result is such result due to features of harmonic approximation in the calculations, in the quantum chemical calculations. If we calculated vibrational spectra IR or Raman, it's not important. For the majority of substances, maybe even for all simple or not simple molecule in different combination of method of calculation and basis set, we found out the same result, and of course it can be corrected by scaling factor, by scaling multiplier, but we didn't use this.
Yeah, but it is a question to your model. It is a question to your model, the accuracy of your model in this spectral range.
This is not, of course, this is not a curative model. We realize that fact, but this is what we see.
Okay. Are there any more questions? Yes.
Okay, I will also recommend to use the Nis shift factor to correct the systematic shift made by this model. But my question is sort of about, you used the CH vibration band of the most of the polymeric molecules as the main source of the shift. But if you measure a lot of substance at the same time, you, for example, try to find particles of this material in some mass of biosample, then you will see a lot of biopolymers that have the similar shift. Can you distinguish this shape from other molecules that also has a long chain of with CH vibrations?
Well, you know, we didn't find any distinguishes between, according to namely CH vibrations, but well, I can see that, well, for example, what about stretching COO, stretching vibrations? We compared, for example, spectra of polylactide and polycaprolactone, and this is well, quite large experimental shift between these. So I hope, I guess, that some similar features we can find out through the CH vibrations if we will need to do it.
Okay, thank you.
Okay, thank you. Are there any more questions? No? Okay, so let's thank the speaker again. And which will be made by Dr. Frolov with a talk diagnosing diseases in dentistry using Raman spectroscopy.
Все.
Которая? Твоя? Все.
Good morning.
Кликни берешь, да, кликни, работаешь. Вот вниз, это лазер.
Good morning. This job was made in Samara University in collaboration with Samara State Medical University. The Raman spectroscopy method is widely used in biomedical applications. Despite its advantages, there is no single universal approach to determine the fluorescence baseline, as well as the problem of decomposition of Raman spectra. For example, the improved modified multipolynomial fitting method is widely used to study biomaterials. The disadvantage of the method is the insufficient degree of polynomial approximation of some forms of fluorescence. Existing methods for decomposition Raman spectra are algorithms for spectra of inorganic substances without complex overlapping of many lines, and they are of limited applicability when working with spectra of biomaterials. The aim of this work was to develop a new algorithm for processing Raman spectra. The task was development of the baseline correction algorithm, development of an algorithm of decomposition, and also testing an algorithm for express diagnosis of periodontitis and assessing the dentin materials during their manufacture. Here we see a general scheme for processing Raman spectra, consisting of the following stages. The first stage is converting units. Later is normalization, smoothing, baseline correction, and spectrum decomposition. Later, we make statistical analysis using machine learning. The proposed baseline correction method is the modification of mod-poly and I-mod-poly algorithms. The main innovation of the developed algorithms are: first, at each iteration, a vector of weights is calculated to approximate the polynomial, which makes it possible to direct the baseline into the region of the local minima of the spectrum. The second is, during the first iteration, high-intensity round peaks with an intensity above the threshold line are removed. The third is the residual deviation is calculated using a new original formula. And the fourth is the new stepping criterion was improved. The weighting coefficients are calculated as follows. First, we calculate the derivative of the current operating spectrum. Then we normalizing it in the range from 0 to 1. And later we normalize spectra is inverted along the y-axis. We see inverted coefficients. The second innovation is that at first iteration is the removal of the intense Raman lines. Dimension of the spectrum becomes smaller after this stage, and in the future the baseline will be approximated to this reduced operating spectrum. The deviation now calculated using this formula. For comparison, we see the formula from IMAT Poly. The calculating the deviation allows us to take into account residual noise and limits the approximation of the baseline below the required level. The user-specified stepping criterion threshold is now used to estimate the line slope angle, which is calculated as the first-degree polynomial as line. Based on the coefficient of determination, it can be seen that the baseline calculated by our proposed method is closer to the simulated spectrum than other. We made simulated spectrum using Gaussian distribution, sum of Gaussian distribution, and compared results to this spectrum. We see coefficient 99.866, which is not bad. Also, the following compression of the spectral area below the intensity under 0 on real data, it can be seen that the proposed method have the smallest area value. Proposed decomposition method. We see here a general block diagram of the Raman spectra decomposition algorithm, which consists of two main stages. First is iterative selection of the line composition for each Raman spectrum and the search for a general model that satisfied all analyzed spectra. The input parameter is an array of analyzed Raman spectra after the baseline correction procedure and parameters set by user. The result of the algorithm is a model consisting of a set of elementary lines with ranges of parameters values that describe the shape of these lines. The preparation stage is dividing the spectrum into independent spectral regions. An example of spectral division we see in this figure. At the first stage of the method is obtaining a set of models for each spectral contour. The resulting model contains information about the number of parameters of elementary lines, which is analyzed at the second stage of the method. The method is based on sequentially adding the number of lines and approximating the resulting model until adding new lines significantly does not improve the model. At the second stage, we create a general model for all Raman spectra. We, for comparison, made also spectrum with sum of Gaussian lines and compared to result obtained by our decomposition method. The mean absolute percentage error of amplitude loss of 3%. Error of estimating the width of the line was 0.29, and the error of estimating the position of the line was 0.11 centimeters. Also, the result of experimental studies of tooth enamel in periodontics using the proposed method are presented. The research material included 50 teeth. All samples were divided into two main groups. First is the group with diagnosis of periodontitis, and the second is the control group. We see significant differences between the two groups in lines of hydroxyapatite. The model was created using linear discriminant analysis. A criterion was being introduced for assessing tooth enamel for the presence of signed characteristics of tooth enamel with periodontitis. Also, we have a threshold value. Below this threshold, the sample is classified as enamel with periodontitis. The accuracy of the method is 89%. Also, using the developed algorithm, the main spectral changes were established and criteria for controlling the composition of the dentin materials during demineralization process were introduced. During the process of demineralization, the relative intensity of the Raman lines of hydroxyapatite decreases, which is reflected in a decrease of the value according to formula, this formula A, which is linear discriminant function number 1. Also, we have a boundary threshold. Above this threshold, the sample is classified as demineralized. Below is mineralized. The accuracy of the method was 100%. And for conclusion, I want to say that all tasks were done, finished. Modified baseline correction algorithm has been developed, and two-state method for decomposition spectral contour also was developed. The developed algorithm was tested on the model for classification periodontitis in tooth enamel and also demineralization process for dentin materials. Thank you for your attention.
Thank you. Thank you very much for the very interesting talk. Oh, yeah, questions, please?
Thank you for your report. When you decompose your spectra, you use equidistant components of decomposition, right? As I can see on the figures.
Distance between.
Equidistance. They are periodical. I mean, the same distance between each peak of each component of decomposition, right?
No, it's not constant distance. We also control this distance. It's a parameter set by user. Is half width at half amplitude. For example, here is 12 centimeters. And minimal distance is 6 centimeters between lines.
And one more question: how do you know how many components do you have to take to decompose the spectrum?
How many lines we have to create? We know it on the second stage. After the first stage, we have a distribution of all module variations of number of lines. Then we use the clusterization analysis using machine learning. Later, we have a set of count of lines, and we choose the most frequently meeting.
Okay, thank you.
Yes.
Thank you. Thank you. Very interesting approach. Please switch back to the same slide with decomposition.
No.
No, discuss. Yes, thank you, thank you. As I understand that you do not use any a priori information about some chemical components which can be responsible for positions of these lines. So my conclusion is that these lines are virtual lines which produced by computer. Is correct?
Yes and no. We also can add some lines in which we sure that they're existing. And also we can verify these lines using libraries and literature sources.
Once again, in the final stage, can you make link of such lines with real chemical components?
Yes.
And you can prove that here real 4 lines, not 3, not 5, and they correspond to some specific chemical components.
As I understand, your question is that big line may consist of some of little.
Yes or no?
Maybe.
Not very soon. Okay, thank you. Are there any more questions? Okay, let's. I have a short question. How many spectras you used for train your system, and then you so at the first stage you have used several samples to train the computer, yes, to find these lines, and how many spectras were used for this?
For example, if we operating 1,000 of spectra, we use all 1,000 spectra for train the model. Then we have one model trained on 1,000 samples, and we use this model to again fit on all 1,000.
So using the same spectra for testing as you use for training?
It's not classifying stage in machine learning. We just take the model for decomposition. We just don't need for testing and train. We don't need to split the all.
But then you test it on to demineralized tooth and another pathology.
Are you questioning on
You were testing? Yeah.
here? Yes, of course. We use the train and test. Of course.
Okay.
I was thinking you questioning about.
Okay. Thank you. So let's thank the speaker again and move to our last talk in this session. The talk will be made by Novikov Vasily, and the title of the talk, Raman Identification of Carotenoid CIS Isomers, DFT Study. So please.
Good afternoon, dear colleagues. My name is Vasily Novikov, and I'll introduce you the work named Raman Identification of Carotenoid Cis Isomers, DFT Study. But my work will be not only theoretical, it will be also experimental. So, carotenoids perform vital functions in the human body and plants. The physical, chemical, and biological properties of carotenoids, for example, bioactivity, depends not only on the structure of carotenoids, so on the type, but also on the configuration of the molecules. Both the structure of carotenoid molecules and the presence of the isomerism affect on the bioactivity, protein activity, and antioxidant and other properties of such substances. Thus, the determination of the chemical and isomeric composition of the carotenoids is extremely important for the medicine, for example, and for the analysis of the food products. Resonance Raman spectroscopy allows non-invasive and non-destructive detection of the carotenoids, including in biological objects and in the very low concentrations. Here on the slide, the carotenoids which were investigated in this work. They all have different structures, as you can see, but also some of them have similar structure features, such as the presence of the ion rings at the end group, or the same end groups, and also the side groups. In the structure of each carotenoid, there is a pollen chain that is alternation of single and double bonds. Such common features lead to the fact that the Raman spectrum of the carotenoids looked the same or similar for each carotenoid. Here, as an example, is the Raman spectra of beta-carotene. And as you can see, there is 3 main bonds. They're in the area of 1000 reverse centimeters. It is vibrational of side CH3 groups. The strong line near 1150 reverse centimeters. It's aligned to corresponding to a single C bond. And the line in the region of 1500 reverse centimeters correspond to double CC bonds. There is a large number of studies on the Raman spectrum of carotenoids. However, almost all of them are devoted to one type of carotenoid, for example, or just for one type of isomers. In our work, me and my colleagues were the first who discovered Raman spectrum markers for certain types of carotenoids and certain isomers of various carotenoids. It allows us to distinguish one from another. Before us, people or authors of the works done this only for few carotenoids and only for the main lines that I told you before. Before, our group also studied in detail the influence of the end and side groups of the isomers types on the Raman spectra of carotenoid. If you talk about experimental setup, we recorded Raman spectra on the microscope Centera 2 with different excitation wavelengths, and the wavelength 532 nanometers correspond to resonance Raman spectra. Some carotenoids cannot be studied in their pure form due to the low thermal and photosensitivity. Therefore, we use DFT calculations to determine the structure and Raman spectra of these carotenoids. We also use these for detailed analysis of the spectra and determination on the structures of all carotenoids. We use, as you can see, Peroda program with a functional loop and a Gaussian basis for that. Samples of carotenoids were isolated by our colleagues from Pushkina Scientific Center for biological research. You can see from what objects they were isolated. It's mainly from different bacteria, and also it was commercial samples which were additionally purified by our colleagues. Here on the slides are presented the Raman spectra of carotenoids which were studied in our work. The length of polyene chains are given in brackets on the right near the name of the carotenoid. As we can see, with increasing of polyene length from bottom to top, the position of the main lines shifts to the lower wave numbers. So it's well-known fact, but also we can see it. Also, I want to pay attention to the line around 1,280 reverse centimeters. All of the samples have this line, and mostly for all of them, this line don't shift. But for two samples, beta-carotene and lutein, this ring shifted by 20 inverse centimeters. It is related to the fact that they all have ion-on ring at the end group. Other samples do not have such. Here you can see it more closely. Despite the fact that this line is not very intense, it is however very clearly visible in both non-resonance and resonance Raman spectra, so it can be used to determine the structure of the end groups. So you can see the difference between two various carotenoids with ring end groups and without them. So we can determine different types of them. To determine the structure of molecules in the experimental spectra, we calculated the structure of trans and mono-cis isomers of carotenoids, as well as their Raman spectra, as you can see on the slide. Here are the spectra of trans isomers of carotenoids that describe the experimental spectra very well. Thus, the experimental spectra samples mainly contain trans isomers of carotenoids, and we also observed the shifting of the lines and this line that I told you before, which can be used to determine the end groups. So we can say that the experimental samples mostly contain trans isomers. Further, using the example of two mono-cis isomers, I want to show you markers which we found to use Raman spectroscopy as a non-invasive method to determine different isomers. Here are the spectra of 9 cis isomers, and due to the presence of asymmetrical side groups on the right and the left hand, some isomers are named by the name with a stroke, as you can see, like 9 or 9-stroke cis isomers. The spectra of these isomers differ significantly from the trans isomers, so they can be distinguished by the Raman spectra from, for example, trans isomers and others. Also, for some isomers, there is no line around 1,140 in reverse centimeters. As you can see, for example, 9-cis neosporin. This is due to the fact that it is cis bond is located on the edge of the polyene chain. So it is we can distinguish not only cis isomers comparing to the trans isomers, but also 9 and 9-stroke isomers. And also we can see the shifts with the increasing of the polyene chain length. Another isomer is 15 cis isomers. All of them are symmetrical because this is cis bond in the middle of the molecule, so we don't have strokes. So it's very interesting features that we observe a line near 1215 reverse centimeters. It is only for these isomers, and this additional line is observed, which refers to the vibrationals of the main chain for the molecule that occurs near the cis bond, near this central region of the molecule. This line is a marker for the detection of the 15 cis isomers in samples. Here you can see the line I told you. For example, in the sample of reaction center of the photosystem 2, we found such line. I don't know. I'm sorry, there is no spectral. I don't know what's happened. So you have to I can't show you. Huh?
To believe you.
Yes. So believe me that we can see this line in the experimental spectra. It's also not very intensive, but it is much more than background. So we can say that in the experimental samples of photosystem 2 in the reaction center, there is a 15 cis isomers, and it is coincides to the other works which determine 15 cis isomers by another experimental methods. So we've made a method that makes possible to distinguish different types of carotenoids and found markers which can be used to determine cis isomers by Raman spectroscopy. And the main results are presented on the screen. So thank you for your attention. I will be glad to answer your questions.
Yes?
Thank you very much. Can you give some more details about the sample preparation? So you said that they were purified carotenoids, but how were they dissolved? Do the spectra depend on the state of hydration state? How many bound molecules of water, of bound water per one molecule of carotenoid?
The samples was isolated from different bacteria and plants. For example, Neosporin, Sphaeroidan, and so on. It was made by just a moment. How it names? No, как выделяли, я вылетел просто. А? No, the method.
Okay.
I'm sorry, it's not my work. It's made by my co-authors, and also we have another samples. It was commercial carotenoids, which was also purified by our
My question
colleagues.
actually refers to do the position of the lines depend on the way how you dissolve the molecule?
No, because they were isolated and purified very good, and we have different sets of samples by commercial of, for example, beta carotene, and also by another plants. So they have the same spectra, but in some biological objects we can see some shifts. For example, is related to the changing of geometry of molecule. So it's the same thing that I want to talk you today, that we can determine some cis isomers and so on.
Unfortunately, Professor Krasnovsky, who was here previous days, has left probably already. Just yesterday he told me that he has made many measurements with different kinds of carotenoids and showed that though they are considered as antioxidants, they generate singlet oxygen also.
Yes,
So
of course.
You know that.
Yes,
And
because it's one of the main feature of the carotenoids. But in pure form, they they can also degrade by ultraviolet and so on, and they can add oxygen and so on. But we have not degraded carotenoids, so
I
they.
see. Okay, thank you very much.
Thank you. Are there more questions? No? Okay, let's thank the speaker again.
Thank you.
And we have a coffee break, so please don't late for the beginning of the next session.
So it's time. We are starting our last section in biophotonics. My name is Daniil Bratashov, and I am glad to invite for talk Vadim Elegin, Приволжский Research Medical University Nizhny Novgorod, efficacy of photodynamic therapy against uropathogenic bacteria. So you have 15 minutes. Okay, let's talk.
Dear colleagues, I would like to talk about our research in photodynamic therapy as an alternative way to control antibiotic resistance or pathogenic bacteria. As you know, as you know, state-of-art lithotripsy techniques crush calculi into dust. In case of infected stones, the bacteria may be spreading through the organ cavity and induce some infection complications. Due to limited penetration antibiotic into organ and wide spreading antibiotic resistance bacteria, a number of infections complications is increased. Antibacterial photodynamic therapy may be used as an alternative approach to eliminate bacteria during lithotripsy. Researchers pay attention to antibacterial photodynamic therapy due to some advanced these techniques such as selectivity, no resistance bacteria, and a lot of targets in the bacterial cells. In this work, we developed antibacterial photodynamic therapy against uropathogenic microorganisms. At first, we isolated microorganism from patient's calculi, and identification species was performed. Next, pure culture bacteria were used for make a collection and developed techniques, for example, adjust laser doses and photoditazine doses. And the last stage, we studied developed regimen on laboratory animals. Okay. First of all, we analyzed isolated microorganism on sensitivity to common used antibiotic. As you can see on the slide, only two species of bacteria were sensitivity for two different antibiotics commonly used in therapy, but all other species were multi-drug resistance. Next, we analyzed an accumulation of photosensibilizer in bacteria. Photosensibilizer used in this study was photoditazine. For this reason, we analyzed and measurement fluorescence intensity of bacterial suspension after various time incubation with different concentration of photosensitizer. And as you can see on the slide, the maximal accumulation was for high concentration of photosensibilizer and and after 50 and 60 minutes. However, during lithotripsy, time is limited. For this reason, we chosen maximal concentration of photosensibilizer and short incubation time for the future studies. At the next stage, we irradiate bacteria suspension by therapeutic laser at 660 nanometers wavelength and analyzed number of viability bacteria. It was shown that gram-positive species were more sensitive for dynamic therapy than gram-negative ones. After incubation with photosensitizers and under ambient light, this species was killed. However, for gram-negative bacteria, the techniques should be optimized. For this reason, we used Triton to increase accumulation photosensitizer in bacteria, as well as output power of laser was increased. As you can see, Triton increased number of killing bacteria after photodynamic therapy. Also, we found that presence photosensitizer in extracellular environment also increased number of killing bacteria. For the next stage, we studied photodynamic therapy bacteria in the habitat. For this reason, we provide photodynamic therapy with photosensitizer and Triton in native arena. As you can see on this slide, in this condition, efficiency of photodynamic therapy was quite good. Number of decreasing bacteria in the culture was at 5 order. So, at the last stage of our research, we evaluate alterations of renal pelvis morphology and renal function in laboratory animals after photodynamic therapy at bactericidal regimes. As you can see, as histological slides, after photodynamic therapy, a minor changes was found in urothelium, like destruction of intracellular contacts and expansion of intracellular space. However, underlying connective tissue was not affected. Okay, the renal test and complete blood count revealed no renal function abnormalities after photodynamic therapy in animals. Thus, this study indicates that antimicrobial PDT is a safety technique that may be used as a accompaniment for antibiotic therapy and surgical treatment of urolithiasis. So the next conclusion may be a draw for our study, such as bacteria isolated from urinary calculi are multi-drug resistance. Triton enhance the PDT efficacy for gram-negative species. Photosensitizer in extracellular environment increases the bactericidal effect of PDT, and PDT may be used for sanitization of bladder and renal pelvis during lithotripsy. Thank you for your attention.
Thank you. Any question? We have time for a couple of questions.
Thank you for an interesting report. And my question is about how do you achieve selectivity of the action of photodynamic therapy? So because your photosensitizer can accumulate not only in bacteria or also in healthy cells, and healthy cells have not so strong membrane in compare with bacteria membrane. So maybe if you have not selectivity, you can kill healthy cells and didn't kill bacteria cell.
Thank you for your question. Our techniques include infusion photosensitizer solution into pelvis or bladder cavity, and the epithelium features of the epithelium exclude penetration of some substance from cavity into cells. These cells may excrete some substance from cells into bladder cavity, but not another way. We studied accumulation photosensitizer in pelvis after 30 minutes incubation photosensitizer in renal pelvis, but we don't found any fluorescence in pelvis epithelium.
Thank you.
Thank you.
And for any other question? Okay, no. So let's thank the speaker again. And we are going to the second speaker. It's Daria Paminova, Prokhorov, General Physics Institute of Russian Academy of Sciences, study of methylene blue interaction with cell membranes, influence on the mechanism of photodynamic activity. So you have 15 minutes.
Okay, thank you for the introduction. Hello, dear colleagues. I would like to thank the organizing committee for the opportunity to make my talk today. And the topic of my talk is the study of methylene blue interaction with cell membranes and its influence on the mechanism of the photodynamic activity. So I will start with a short introduction. Of course, you know that the treatment of oncological diseases is of great importance. And okay. No, I will speak louder. Okay. And today there is a continuous search of new approaches for treatment of oncological diseases. And one of them is photodynamic therapy. Just to remember, for photodynamic therapy, we need three components. These are photosensitizer, light, and oxygen. And photosensitizer absorbs the light, and then we have two possible routes. Type 1 photochemical reaction, this is electron transfer reaction, which initiates the formation of hydroxyl radicals. Or type 2 photochemical reaction, which is the energy transfer to molecule oxygen and singlet oxygen creation. These oxygen species are very cytotoxic, so as a result we obtain necrosis or apoptosis of exposed cells. PDT has several advantages such as non-invasiveness, high selectivity, minimal side effects, but this method is limited by the light penetration depth into biological tissue and also by the oxygen content, especially for type 2 pathway. And I should mention that vast majority of clinically approved photosensitizers utilize the type 2 photodynamic reaction. So PDT of tumors which are in hypoxia state is challenging. And the type 1 photochemical reaction may be preferable for the therapy of such tumors. Therapy of hypoxic tumors is challenging not only for photodynamic therapy but for all treatment methods, and at the same time it's very important to treat such tumors because they have very poor prognosis for survival for patients with such kind of tumors. Tumor metastasis and drug resistance frequently happen under hypoxic condition because hypoxia is one of the driving forces of so-called metabolic reprogramming. Hypoxia strongly influences the tumor microenvironment and leads to bad prognosis, to expression of vascular endothelial growing factor, polarization of tumor-associated macrophages, and also expression of hypoxia-inducible factor. All these lead to bad prognosis. So, as I say, for photodynamic therapy, we need photosensitizer, and one of promising photosensitizers is methylene blue. Methylene blue has both photodynamic activity and redox and catalytic properties. It has fluorescence in the red part of spectrum. It's important for the good light penetration into tissue during PDT. Depending on the environment, it means solvent, ionic strength, pH value, and so on. It can form both singlet oxygen and other reactive oxygen species. And also, according to the literature data, methylene blue is capable of increasing oxygen consumption by tumors. It's also good for photodynamic therapy. So this photosensitizer is very interesting, but it's quite hard to study it. Because oxidized form can be easily reduced to the colorless form in the absence of oxygen or by interaction with NADPH or reduced glutathione. Generation of singlet oxygen decreases during dimerization of methylene blue. And the ratio of monomer to dimer strongly depends on the solution composition and concentration. In water, in aqueous solution, the aggregation is also sensitivity to the ionic strength on this, of the solution. So the salt concentration is of great importance. And also pH influence the singlet oxygen generation efficiency. So, to conclude, a large number of interrelated factors affecting the photophysical and photochemical properties of methylene blue and make it difficult to study and implement it in clinical practice, despite a number of unique properties. For clinical use, it is important to study the photophysical and photochemical properties of methylene blue under conditions which are closest to the real biological ones. So in this regard, in this work, we study the singlet oxygen and another reactive oxygen species generation efficiency of methylene blue in vitro using spectroscopic methods. We have started with a study of aggregation of methylene blue in different biological media. We have obtained the absorption spectra for different methylene blue concentrations in water, sodium chloride, RPMI media for cell cultivating, and also in serum. So characteristic peaks were observed in the spectra. This one corresponds to the absorption of monomer, and this band corresponds to absorption of dimers. And you can see that by the increase of concentration, we can obtain the increase in dimers absorption attributed to increase of dimers concentration. So the changes in the absorption spectra for water begins at a concentration about 3 milligrams per kilogram. And for RPMI and serum, the changes begins at concentration of methylene blue about 10 milligrams per kilogram. So this experiment allows us to know which concentration we can use for cells without aggregation. Here is the dependence of monomer to dimer ratio of methylene blue on the concentration. And you can see that in water, the most rapid increase in aggregation was observed. And in serum, dimer monomer ratio was quite low in the studied concentration range. So this concentration range can be used. So the next step was the assessment of photodynamic activity of methylene blue in vitro. According to literature data, the singlet oxygen generation quantum yield is quite high, about 0.5, but this value was measured in isotropic ethanol solution. So we use another method which allows to study photodynamic activity in vitro. Here's our setup. We use a fiber optic spectrometer to measure the diffuse reflectance spectra and analyze the hemoglobin absorption. Knowing the difference between absorption of oxidized and deoxidized hemoglobin, we can calculate the oxygenation of our sample, which consists of erythrocytes, serum, and photosynthesizer. Then we begin to perform PDT. Photosynthesizer, if it produces singlet oxygen, if a photosynthesizer produced singlet oxygen, the amount of oxygen in the media decreases because singlet oxygen irreversibly reacts with microenvironment. Hemoglobin acts as donor of oxygen and begins to deoxygenize. So knowing the deoxygenation rate for studied photosynthesizer and for knowing photosynthesizer, we can calculate the relative quantum yield. Here we use aluminum phthalocyanine as a reference with a well-known quantum yield of singlet oxygen generation. And here are the obtained results. So you can see that in the investigated range of concentration, the efficiency of singlet oxygen generation was very low. And we assumed that it can be attributed to binding of positively charged cationic methylene blue to the negatively charged cell membranes. So next step was to check the generation of another reactive oxygen species in vitro. So we performed it on HeLa cells which were incubated with methylene blue. And then we use the special fluorescent indicator, live rose, to study the reactive oxygen species in vitro. The cells were examined using laser scanning microscopy, and the intensity of fluorescence of indicator was measured. And here are the results. You can see, if you can see, that in control sample we don't have the fluorescence of indicator. Here are only the nucleus of cells which are stained with DAPI, and after adding of methylene blue, we obtain green luminescence of indicator, and after irradiation, the intensity of this luminescence increases in vesicles which are very bright, if you can see, of course. This method allows us to confirm that we don't have singlet oxygen generation, but we have another reactive oxygen species which were generated by methylene blue. And also analyze the cell death type after PDT with methylene blue. We use the concentration 20 milligram per kilogram, 2 incubation times. The irradiation was performed with laser light with 660 nanometer. The pumping power density was 100 milliwatts per square centimeter, and we used doses 50 and 150 joules per square centimeters. After PDT, we wait about 24 hours and then stain our cells using annexin 5 and propidium iodide to analyze the cell type death. cell death type, sorry. So here are the obtained results. You can see that without irradiation we have no effect. Then we obtain the cell death, and this effect is dose dependent and also concentration dependent, accumulation type dependent. It was shown that at all studied irradiation doses and accumulation times, the predominant type of cell death was apoptosis. So this confirms that the type 1 photodynamic reaction can be used to obtain a cytotoxic effect in our case. So I will proceed to conclusion. The efficiency of singlet oxygen generation and photodynamic activity of methylene blue were studied in vitro. In the investigated range of methylene blue concentration, the efficiency of singlet oxygen generation was rather low because positively charged methylene blue binds to negatively charged cell membranes, which lead to a change in the type of photodynamic reaction. The emergence of other reactive oxygen species different from singlet oxygen in cells has been demonstrated. And the generation of reactive oxygen species and the low quantum yield of singlet oxygen generation indicate the tendency of methylene blue to provide the type 1 photosensitization mechanism rather than to type 2 mechanism, and in biological media and in vivo, and it could be very useful in the future for the photodynamic therapy of hypoxic tumor, as we hope. So thank you for your attention and for your time.
Thank you. Any questions from the audience?
Okay, thank you for interesting talk. My question is about, thank you, about, did you estimate the action of the light with 150 joule per square centimeter without methylene blue?
Yes, this is
control? Or
yes.
Yeah.
Thank you for the question. This was a control group. It means radiation without methylene blue.
Well, interesting results. Thank you very much for your presentation. My question is, do you have any idea why apoptosis but not necrosis is induced in vitro in these therapeutic regimens? And can we expect apoptosis in vivo in mouse tumors?
Thank you for the interesting question. I think that in our case, apoptosis is caused by the low dose. These irradiating doses are quite low, and I think that their accumulated concentration is also low. Usually we expected necrosis by the strong irradiation with high concentrations. We don't study this effects in this work, but we have such study for another photosensitizer, and usually the dependence is the same. At high doses of photosensitizer and the radiation, we obtain necrosis, and at low doses, apoptosis.
Thank you.
Thank you for an interesting report, but photosensitizing properties of methylene blue have been known for a long time. What's the novelty of your work?
Thank you for a question. As I mentioned, the study of methylene blue in vivo is quite challenging because, of course, I perform research in the literature, and all the papers say the methylene blue has a high efficiency of singlet oxygen generation. So I was very surprised when we obtain a low amount of singlet oxygen. A lot of studies are dedicated to methylene blue, but not so many studies was performed in vitro and in vivo. So I think this is the reason why such well-known dye is very poorly used in clinical practice.
But methylene blue is very small molecule. And how do you achieve selectivity? Because this is very challenging to achieve selectivity.
Thank you for a question. Usually for in vivo, we achieve selectivity but adjusting the accumulation time because the metabolic rate of tumor and normal tissue are quite different. And for methylene blue, we have observed some interesting effects because the accumulation of methylene blue in tumor is quite different to the accumulation of methylene blue in normal tissue. It's in vivo, it very fast undergo to Laker form. And this is the question how to prevent it now. But the difference is very high. Yes.
Okay, so let's thank the speaker again. Okay, our next talk is given by Alexey Popov, Samara University, and the topic of this talk is fluorescent analysis of photosynthetic organisms, stress resistance in different conditions.
Dear colleagues, I have adjusted the presentation a bit. It's another short report on visualization, so I hope the visualization will be visible. Sorry for the pun. From the general, we may put it as global perspective. The energy gets into the living systems through light. We can say that's not the only way, but it is certainly the main way. If we give the ecosystem view a bit of a practical perspective and some consideration, we may not notice that you don't have to be a producer to use light as an energy source. We can find phototrophic organisms among the consumers and decomposers. There is no statistically reliable correlation between the energy flow and the stability, for instance, of the ecosystem, but we, from the practical perspective, can be maybe interested in the increasing of the energy flow from the system, through the system, sorry. It works pretty much the same in both natural ecosystems, classics, and artificial ones. For instance, this is one of the European projects on the closed ecosystems created in order to provide a small crew of human beings in a closed space. In this case, I mean space, not outer Earth, out of beyond the Earth, but closed space even within the Earth condition. And as we can see in this semi-artificial ecosystem, the light brings energy to the producers and to the decomposers alike. We are used to green phototrophs, for we all love flowers, plants, and so on, whatnot. If we extract red and blue, the peaks, from our RGB vision, we get green. So we get green plants, but phototrophs don't have to be green. They can be greenish with other peaks of absorption spectrum. They can be yellowish. This is only the way to avoid excessive energy going through the light harvesting systems, so they can be preserved from damage. Visible light can also damage any complex molecule and complexes of molecules. We can also use the light beyond the visible part of the spectrum, near ultraviolet, near infrared. We can use it to the different degree. We can also use the wavelengths that are so carefully avoided by usual classical photosynthetic organisms. I mean, if we take non-chlorophyllc phototrophs like halobacteria, or to put it more correctly, haloarchaea, we can use the part of the spectrum usually avoided by chlorophyll-bearing photosynthetic. What can these organisms give us as bricks, as building parts for our artificial ecosystem, no matter where do we want where we want to use them? They can tolerate years of freezing, not only years, 100 and even 1,000 of years of freezing, so they can be switched on and off in conditions needed. And hydrobiosis, they can live without water for years, for tenths of years, and so on. Radiation resistance, which is especially important during the space travels or in some in the sites of technogenic disasters. They can tolerate extreme salinity, which is very important, for instance, to purify the products of our body metabolism. They can be toxin resistant and so on. So, all in all, we get, what can we get almost for free? From the viewpoint of energy usage, food, fuel, cleaning of the environment, whichever that would be on Earth or on some kind of space station. We can synthesize bioactive molecules up to the medicine. We can obtain electric power. We can use nanostructures of the photosynthetic organism for our purposes. Emotions, aesthetic, and design can be not that important on Earth, but important still, but they can be very important in space, in closed compartments where people are naturally stressed. Of course, remediation and making the media more or less stable, and it's invaluable biotechnology, as said. So, come on, no? Beg your pardon. Sorry, dear colleagues. No matter, perhaps we shall just skip some of the information. The conference is coming to its closing to its end, so let's just skip it. I don't know what has happened. Nevertheless, in space we can only imagine. There were some experimental data and visualization. Oops. Anyway, I'd like to mention that we can use two approaches to the experimental artificial closed ecosystems. Some of them are classical. Sorry, I haven't brought any. They need to have a system of sensors. So we have a closed container and a set of sensors put into it. We realize that it's a certain risk. The ecosystem can't be considered closed, 100% closed. But we also can vacuumize the ecosystem completely, like this way. Even a logger may be put inside to get data from the inner medium. But sometimes, if we take, for instance, relatively cheap nano-satellites or microsatellites, we are strongly limited by the volume and size of the container. For instance, it can be 1 or 2 milliliters. It can be of different shape. It can be Eppendorf test tube sized. So we physically can't put any logger or sensor in it. So the particular problems are set of species. If you have 10, you have already countless combinations. If you have 50, it's far worse. Plus, you might add human being, its micro symbionts on the skin, mucus, intestines, whatnot. It's a zoo, and the zoo should be observed and controlled. Containers of different shape, chemical composition, and whatnot, light, sources, spectrum, and so on. Other physical factors. Space travel is a tricky thing. It's a great stress event for any organism, and some of the experiments are even devoted to just putting organism out of the Earth atmosphere and returning it back, and then genetic analysis and whatnot. It is an event for any organism by itself. And of course, medium substrate. It can be solid, liquid, spongy, granulated, whatever. So we have main conceptual problems, number of combinations, countless, endless, and data gathering versus experiment duration. Our experiments sometimes can be prolonged for years, months and years, but as soon as we open the container to get data, the experiment is over. So we have to find some other approach, and optical methods can come and be of great, can come to help us and to be of great use. The simple experimental device, the main objective was to visualize, not only get numeric data, but visualize the information. Initially, I thought as much. Initially, it was developed to measure the quantity of glycation, advanced glycation products in human skin of people of different age, with or without diabetes, immunosuppressed, immunocompetent, whatnot. So, as you can see, it's sizable, quite compact, even in its present experimental state, preliminary state. Usually it gives two types of image, in white light and in UV, ultraviolet light. So if we get strictly numeric data, like in several commercially available devices, for instance, artificial fibers, hairs, dust, dirt, hematomes, whatever, can influence the numerical data. some kind of impurity. In the normal condition, it should be it should glow with a bright blue up to white color. And of course, there are some formations on our skin, nevi, moles, hyper or hypopigmentation and whatnot. And they can be numerous, and they can also influence the results of human skin testing. Back to our photosynthesis. Where is it come? When will it come at last? Here is the crude chlorophyll extract. It should be bright red. And here is the fluorescence of pure cellulose. It should be bright blue. Now, I'll present several images of stressed photosynthetic organisms. Healthy terrestrial plant leaf after exposition, several hours of exposition to ultraviolet, and dead leaf, dead because of the radiation. So we can see that the photosystems of the plant organism were completely, utterly destroyed by the radiation. The same view can be obtained after representing to visible daylight for a longer period of time. We also can see not only the fact of destroying of photosystems, but we can see where the large organism is damaged. We can see that it dies here, but it still holds on here, and then death. Of course, plants are cute, but not 100% useless, but close to that. They're too large, their adaptation skills, so to put it, are limited. So algae and bacteria are our everything. For instance, in normal condition, we should observe different algal colonies of different age. Green algae, they have normal cellulose cell wall. Red glowing, red-pink glowing with blue infusions. And we can see old colony, mort mass of the dead algae, dead cells, and we can see that the colony is still living. Very interesting are the drought-resistant, desiccation-resistant organisms. Some organisms can be dehydrated and then rehydrated again. Active moss. It should be bright red. Now, desiccated moss without any water. We can see it's still alive. We can reactivate it. And here is a dead moss. Believe me, there are blue lights, dark blue lights. Sometimes we can get some paradoxal pictures. This is the healthy cyanobacterial colony. This is dead colony. Living cyanobacteria generate ultraviolet protecting and absorbing substances, cytinamine, mycosporin-like amino acids, and whatnot. And as soon as the organism dies, we can get the fluorescence. So I've shown you that we have to be sure that the ecosystem is closed. We have to vacuumize it. We get one layer of polymer, gas, dirt and whatnot, another layer of polymer or glass container, and medium. Sometimes the medium is black. So we can't use a simple camera to visualize our organisms. So we can use fluorescence again. Unfortunately, this pattern of the container and vacuumizing polymer is not seen here, but you can see algal growth in a closed ecosystem. Not everything goes smooth. For instance, organic medium is okay, it's blue. We can see, for instance, halophilic algae here. It's pink to red, but for instance, if we can take very perspective of organisms like halobacteria, haloarchaea, which have another type of photosynthesis, we get some black spots. We can't see the thing, we can see in a visible light. And purple bacteria are also give a strange and curious picture. Crude carotenoid extract is also almost black. It's crude, that's why it has faint red glow. So, allow me to conclude. The optical methods and the experimental device, which was designed initially for measuring of advanced glycation products in human skin, is can be quite usable for basics, for preliminary stages of space experiments with closed ecosystems, and finding out how one of the most important of the members of ecosystem, photosynthetics, function in different stress conditions. It can be done swiftly, quickly, without any contact, and it's quite informative despite the preliminary nature of the experiment. Thank you for your attention. I will be glad to answer some questions if you have any.
Okay, we are sorry, but let's thank the speaker, and we are out of schedule, so maybe I will introduce the next speaker, and those who want to ask questions, you can ask in background. The next speaker is Marina Alexandrovna Sirotkina, and the invited talk, optical visualization of biotissue microstructure and microvasculature in norm, pathology, and after treatment. Приволжский Research Medical University, Nizhny Novgorod, Russia.
Okay, dear colleagues, I'm happy to be here, and thanks the organizing committee to invite me. And my presentation today about optical coherence tomography and its application in pathology, norm, and during therapy. So, and I'll start with some words about custom-made optical coherence tomography. So, spectral domain OCT was developed in Institute of Applied Physics in Nizhny Novgorod, and this slide demonstrates you technical characteristics. And it's very important that we can investigate structure, elastic properties, microcirculation in one point of interest. Very quick, up to 26 seconds, label free and real time. And I'll start today only on OCT angiography modality, and see you may see some images. I should say that OCT angiography can visualize capillaries, arterioles, and venules, but can't differentiate it. And also OCT can't measure speed of blood flow, but we can visualize vessels with blood flow. So you may see normal mucous, brain, and intestine, and experimental tumor model. And today I say about how we applicate OCT for tumor study and control the therapy of PDT, chemotherapy, and radiation therapy. First of all, we formulated some condition to apply OCT for clinical application. First of all, we choose optimal objects for OCT is transparent tissue. It may be mucous, brain, skin, and tumors. Secondly, we must have a direct access. It may be gynecological tract, oral cavity, or intraoperative access. And so thirdly, to avoid motion artifacts, we have to use special OCT holders. But we believe that OCT angiography is a useful tool for treatment assessment or for tumor assessment and monitoring of anti-tumor therapy. And I'll start with some experiments where we we monitored tumor development. The study was performed on ear tumor model, and you may see that tumor growth associated with increasing of blood vessel density, and especially it's associated with increasing of capillaries, percent of capillaries in the tumor. And it was validated by histology. So also we try to differentiate for subtypes of basal cell carcinoma by OCT, and we formulated some features for each subtype. So we investigated nodular subtype, nodular with necrotic core, superficial, and sclerosing subtype. So usually nodular subtype have tree-like branching capillaries, dilated capillaries. Nodular subtype have vascular free region, which correspond to necrotic core, and superficial carcinoma have thin and thick branching vessels with irregular vascular distribution, and the sclerosing subtype have the densest vascular network. So OCT can differentiate all subtypes of basal cell carcinoma based on architectonic of blood vessels network. After that, we treated the ear tumor model by anti-angiogenic therapy with bevacizumab, and we monitoring during several days, and you may see that in 5 days post therapy by bevacizumab, only a few vessels we can see on OCT images, and in 7 and 9 day, blood vessels absolutely disappear from OCT images, and it was validated by immunohistochemical images and fluorescence imaging. And now I'll turn to monitoring of PDT. So, as you know, PDT is very complicated very complicated method. And can we control all steps of PDT? Of course not, but we have a tool which help us to control vascular reaction to PDT, and we believe that it's maybe very helpful. And from literature we know that 24 hours post PDT reaction, vascular PDT reaction developed during several hours post treatment, and the key time is 24 hours, because in 24 hours in 24 hours post PDT, thrombosis and hemorrhage usually occur in tumors, and vessels absolutely disappearance from OCT. So again, we perform investigation on ear tumor model, and we choose a mild regime of PDT to obtain two variants of responses, complete and partial responses. So in control group, you may see well vasculature imaging, but in group of responders, in 6 hours and especially in 24 hours, we can't visualize any perfused vessels. So OCT OCT is very sensitive for blood perfusion interruption, and it was validated by histology again, by immunohistochemistry and fluorescence imaging. Also, we perform quantitative analysis of these OCT images, and we can formulate it very reliable criteria of PDT responders. If we can visualize any vessels in the tumor and visualize only 1% of perfused vessels in peritumorous areas, so PDT is successful. If not, PDT is non-successful. And we try to test this criteria on patient tumors, basal cell carcinoma. And I should say that the criterion was the same. So in 24 hours post PDT, we absolutely have no vessels in the tumor, but we have a little bit more vessels in the peritumorous area, 1.4%. But OCT can predict the PDT successful in patients with diagnostic accuracy of 93%. Again, the problem with presentation. Oh, so next step, we apply PDT to non-tumorous pathology. It's lichen sclerosis, vulvar lichen sclerosis. It's inflammatory autoimmune disease and affect blood vessels and connective tissue. So we applied OCT angiography to monitor recovery of tumor, or recovery of vessels. So maybe this slide more informative. We calculate, of course, blood vessels density parameter, and you may see that I should say that we obtained two reaction to PDT in this disease, complete and partial. And in partial responders, we can't no recovery of tumor was found, and blood vessels stay in the low level. But in case of responders and complete responders, structure of tissue recover, and vascularization was very, very good and close to a normal level. So OCT can control not only PDT reaction to therapy, but monitoring the tumor recovery post-PDT. And now I'll turn to chemotherapy monitoring by PDT. And we compare two drugs, bevacizumab and cisplatin, and I should say that cisplatin didn't affect vascular, and we know about that. So OCT angiography is useless for this condition. And now one example about OCT application to radiation therapy. So radiation therapy we applied to patient with head and neck cancers, and we detected development of mucositis, 1, 2, and 3 grade of mucositis. And I should say that mucositis is a very strong affect the oral cavity, and a big problem for patients. So OCT angiography based on vascular density parameter can predict the development of mucositis 1 or 2 or 3 grade on 1, 2, or 3. So it's a very helpful tool. And to summarize, I should say that OCT angiography is a promising, non-invasive, label-free, and real-time approach to study of tumor development, anti-tumor therapy, and monitoring of effects of PDT, not chemotherapy, PDT, radiation therapy, and tumor and tissue recovery. So thank you for your attention. Excuse me for technical problems.
Okay, let's thank the speaker. Any questions?
Thank you very much for the presentation. My question is, how did you conduct the monitoring of the state of the tissue, the level of destruction of the vessels after PDT, and the recovery rate? Was it just visual control, or
histological,
or did you use any elements of machine learning algorithms for this?
Thank you for a nice question. We only dream about machine learning. We don't have now. Only visual, only histological comparison, and quantitative analysis of OCT images.
So one must have a lot of experience in
we have
estimation of the effects. Yeah?
We have yes.
Good for you.
Okay.
nice talk. In your clinical studies with different types of skin cancer, what was the selectivity and specificity for differentiation between different cancer types? Skin cancer.
Oh, thank you very much. You mean basal cell carcinoma, subtypes of basal cell carcinoma. I didn't say about that. It's about less than 90%. 90, about 90, да. Yes.
Okay. Any other questions? If no, then let's thank the speaker again. And we are finishing our last section of Biophotonics. We will be glad to see you in Saratov at the Saratov Fall meeting next week.
May I say a few closing remarks as responsible for this part of the conference? Well, I think it is a general general estimation that the section was a success. We had quite a lot of papers, high-class papers, and we worked during 3.5 days all through the conference. So our section of Biomedical Photonics is second largest section of the conference. Just a few papers less than in the largest section of laser matter interaction. So this means that biophotonics develops and the level of the talks also gets higher and higher. This time, first in the ALT conference, we had a Russian-Chinese workshop on biomedical photonics within the section. And though we had some technical problems with internet connection and with the too much light in the audience, so that some images were hard to see, still we think this is a general opinion that this workshop was also a success. The continuation of the Chinese-Russian workshop will be in Saratov in a few days during the Saratov Fall meeting. And in general, this subject, this area of research, biomedical photonics, is growing. Earlier this year, we had a very nice workshop on biomedical photonics within BRICS countries. All initial members of BRICS, 5 countries, all had representatives at the workshop, and this was also a high-class workshop. So, biophotonics is alive, it grows, it develops, in spite of all problems that we have. We have problems of interaction with foreign collaborators, but still we do our best to overcome that, and this gives us confidence in future development and that we shall have further success. So I would like to thank all the participants of this session, and not only this session but this section. Yes, and just in a few minutes we shall have a closing session, and there it will be announced, given information about future conference, and probably even plans for future other conferences, and I invite you to participate. Thank you very much again.
Thank you.